So today we are going to start the discussions on the emerging non-volatile memories individually. So we talked about those emerging non-volatile memories in the earlier section 6, but that is like a high-level overview. So today we are going to dive deep into each of those technologies. And then today we will first talk about the RRAM, resistive random access memory. So this is an outline of today's lecture. So first, some brief introduction about the RRAM technology, and then we will use some representative device data from two of the research institutions. One is E3, one is IMEC, to showcase how the device parameters or characteristics look like. And then we will talk about the physical mechanism of the RRAM operations. And finally, we will talk about some array-level integration issues and also the recent macro chip demonstrations from the industry. So first of all, RRAM, resistive random access memory. So actually, I started this RRAM research about like 2007. It's already 17 years. So I got my recognition in the field, largely because my early days, the contributions to this field. So I know the history of this technology, and I know how the technology, came from the research papers all the way to the industry offering today. So here, at the high level, actually, there are two subcategories of the RRAM technology, and we can classify that into two device types. The first one is this oxygen vacancy-based RRAM, or sometimes people call it OX-RAM, oxide-based. So basically, here the mechanism is due to the filament formation within the oxide layer between two electrodes. And this filament is made of the oxygen vacancy. So after you take out the oxygen atom from the lattice, then one vacancy is left there. So if you have a filament made of those vacancies, then you can conduct the current between those two electrodes. Therefore, you have this no resonance state. If you break up this filament, then you will get the high resonance state. So the other type is called this conductive bridge random access memory, CBRAM, which is made of this metal ion diffusion into the solid electrolyte. Could be oxide, but the key difference is that the filament here is made of metal instead of oxygen vacancy. Okay, so here we can have the electrode, and we call it active electrode because here those electrode materials, typically like copper or silver, could easily diffuse into this electrolyte. Therefore, we can create the metal filaments between those two electrodes. So that's the difference between those two. The filament composition is different, but other than that, the operation principle is very similar. So here, this is the typical current versus voltage IV characteristics of this oxide RRAM. Actually, the data here is obtained from the devices I fabricated at Stanford clean room, many years ago. So I measured the IV from this two-terminal device, and then this is how it looks like. It's very representative. This is like a bipolar IV, and then initially the device is in the high resonance state. Therefore, here when we ramp up the voltage, then the current is low. So here the current is in the log scale. Okay, then the current is low until some threshold. Then the set operation happens. The current jump, and here typically we'll apply some complex current to prevent the permanent breakdown of the device. So here we limit the current, let's say 100 micron from the equipment Also, you can do that from a transistor. You just provide the maximum current that you allow the device to pass. So then we sweep back, then the device is in the low resistance state. And then if we want to reset the device, we have to apply negative voltage. And then reset is kind of gradual. Then the current keep decreasing. And then if you sweep back, the device goes back to the high resistance state. So you see that the set process is kind of abrupt and reset is kind of gradual. So here, those definitions, I think we have talked about that before, so I've skipped that. Sometimes we use HRS, LRS as a short form for this high and low resistance states. And also we talk about the CB-RAM, which is another type. So in this case, in this example, right? So here the saver electrode is active electrode. So saver, once you apply positive voltage, then that will be oxidized. Then the saver ion will be driven into the electrolyte here. And the electrolyte could be oxide, but also there are other materials that could allow the saver to diffuse. So for example, chalcogenide and even nitride, amorphous silicon, amorphous carbon, and even polymer could allow the saver to diffuse, okay? So once the saver is diffusing from one electrode to another one, it will deposit on the other electrode. And then the filament will grow this way. And then once the filament, connect those two electrodes, then the current can flow, then you jump from low resistance state to the high resistance state, okay? And then if you reverse the voltage polarity, then the diffusion will go the other direction. So you will dissolve the filaments, and then device goes back to the original state. So this is the typical mechanism. And in terms of the material choice, let's say for the OXRAM, so this was actually a survey I did earlier. This was already many years ago. But even at that time, there are like dozens of oxide materials have been reported in the literature that they can show this resistive switching behavior. So here, also the blue element is typically the electrode material we are going to use for the oxide run. So here I highlight a few elements, okay, like hafnium, tantalum, zirconium, aluminum, because those are widely used later for the industry development, because those materials are more compatible with the CMOS fabrication, because many of them, for example, hafnium oxide, have already been used in the high-k metal gates process. So this is friendly to the industry. But of course, research groups, explore, exotic elements. So here are the key attributes of the RRAM. So here, the read speed could be as low as 10 nanoseconds. Programming voltage typically up to 3 volts. And then programming current, let's say tens of micron to 100 micron. And then cycling endurance, vary or not, from 1e6 to 1e12, let's say million to trillion cycles. And then retention could be good at 85 degrees C and more than 10 years, of course, extrapolated. And then people have demonstrated small devices, less than 10 nanometer in terms of the cell dimension and the electrode size, okay, for the memory element itself. And then I talk about the material choice to be compatible with CMOS. And then also the fabrication temperature is also under the thermal budget for the back-of-line integration. Typically, people nowadays use ALD, atomic layer deposition, at like 200 degrees C to fabricate those oxides. So here, those numbers are representative. That means not necessarily all those numbers will show up in one device, okay? This is a general range, right? So not necessarily one device will have all those numbers together. So there will be some trade-offs, right? For some devices, maybe the endurance is good, but the retention is not that good. So then there will be, trade-offs depending on the materials. So next question.
Between oxygen RAM and the metal RAM, is there anything that is better? Was there any
Okay, that's good question. Between the oxide RAM and the CB RAM, so I would say oxide RAM may be a little bit better in terms of the reliability, like the endurance and potentially retention. So that's why, and also like from the variation point of view, maybe a little bit better. So then the CB RAM advantage, one advantage could be the on-off ratio could be larger. Okay, the high resistance versus low resistance states, the resistance ratio for the CB RAM could be in more than thousands or even tens of thousands. But then the oxide RAM's on-off ratio maybe only a few, less than 10, maybe 10 to 100. But then after so many years of the R&D, industry prefer to use oxide RAM. So for the we are going to show the foundry offering later, but most of the commercial offering today is based on the oxide RAM. Yeah. Okay, so we will show some device data from the E3 and iMac. So this was a very early prototype of this 1T1R technology from the E3, which is Industrial Technology Research Institute in Taiwan. And this was published at IEDM 2008, where I just started on this research. So we learned a lot from this paper. By the way, the first binary RRAM paper published by Samsung 2004 IEDM. That was regarded as the first publication in the binary oxide. In that case, that was a nickel oxide. Many troubles with the nickel. So later, let's say, E3 was the very first research organization that switched to hafnium oxide. And I can tell you today, TSMC is using this one, okay, hafnium oxide. And everybody is using that actually. Not everybody, I mean most, I would say most foundry is using this one. Let's say, or maybe a variant of this one. Let's put it this way, okay. So anyway, so this was the very first demonstration. And you see the stack here is titanium nitride is an electrode material. It's conductive, okay? It's like metal, maybe a little bit higher resistivity than metal, but it's quite conductive. So this is widely used as electrode. So here the hafnium oxide is a switching layer, and then here the key innovation is to have this capping layer, they call capping layer, interfacial layer like titanium here, adjacent to the hafnium oxide. So this is key, okay. So this titanium is very, let's say, this titanium layer could attract the oxygen from the hafnium oxide very easily. So that means you are going to oxidize the titanium a little bit. Maybe you can create some interfacial high oxide. Then what is left over here in the oxide, hafnium oxide, is oxygen vacancy, this oxygen vacancy, okay. So the titanium is helping to create the oxygen vacancy in the hafnium oxide because titanium, gets some oxygen from hafnium oxide. So here, this device dimension is already small at that time, 3 nanometer, 30 nanometer in diameter, okay? And the thickness here, you can see that it's probably 5 nanometer or 6 nanometer for the hafnium oxide in terms of thickness. So this device was integrated at a 180 nanometer CMOS at that time. So here the transistor is a 180 nanometer transistor, and then the resistor is here is pretty small. You see here the diameter is only like 30 nanometer. So the limiting factor is not the memory, it's the access transistor, okay, in terms of the area. So here, this is a typical IV characteristics. You see this is pretty much like what I fabricated from Stanford clean room. So you see this bipolar switching, right? Very representative. By the way, the materials that we used, I used as a Stanford clean room was also hafnium oxide. So at that time, we realized that this is a good material. So anyway, so here you see that this is this bipolar switching, and then here the switching voltage actually is kind of low because of that titanium helped to create the oxygen vacancy. So then you see that the turn-on voltage is like 1 volt. And then here you can keep cycling this. So here this is endurance data, cycling endurance. You apply positive and negative pulses, let's say positive 1.5 volt, negative 1.4 volts. And then you measure the resistance after the positive pulse and negative pulse, right? Then you can measure the resistance. So if you measure the resistance, then you will get the resistance as a function of the cycling endurance. So here you see the on-off ratio, like more than 100 maintained over 1E6, 1 million cycles. Okay, so the endurance is good, at least 1E6 cycles.
So the characteristics of 1T1R and the 1R are similar, right? So I was just wondering what is the reason that
Oh,
it happened.
I should ask this question for you, right? You have learned that. That would be your exam question. Why do you need the transistor there? You should not ask me. We already talked about that in the section 6, right? So you can answer for him.
Is it because like we have the selector to increase the LRS resistance or something like that? Like
No, you have to think about the array integration, right? Without access transistor or selector, how can you cut off the sneak path? Okay, ask yourself. So the switching speed. So here they have done some fast pulse measurements. So here the set and reset could happen even below nanosecond. Of course, they need some special setup to minimize the parasitics from the cabling in the instruments. But here you see that the switching happens even down to 300 picosecond with not enough voltage. So potentially this could be fast. Of course, this is a function of the voltage. You apply higher voltage, it's switch faster. And then here the retention, for example, here they bake the device at 150 degrees Celsius and then monitoring the resistance high and low. And then after like here maybe 1 day or few days, then they extrapolate to 10 years. But this is not good way to the extrapolation, right? If you recall, when we talk about the NAND flash, for long time memory, you have to do what? Question for you. Retention test. What is the standard way to do the retention test? Assuming the physics is governed by the thermal process. You have to vary the temperature and then, do the temperature accelerated aging. So anyway, so this was some early work demonstrated the potential of this device. And also here, since the on-off ratio is large, you can achieve this multi-level cell operation, okay? So here what they showed here is to, for example, change different reset voltage, right? When you sweep back, you stop at different reset voltage, then you can create multiple states, multiple resistance, right? States. And also in the set operation, you can use different compliance currents to limit the current. Therefore, you can create different resistance levels as well. So in the 1T1R configuration, you can do this with varying the gate voltage of the transistor. Because the gate voltage, different gate voltage, the transistor's drive current will be different. So the maximum current you're allowed to pass the transistor will become this compliance current. Therefore, you can, by changing the gate voltage of the transistor, you will change different compliance current. You will get different resistance levels of this RRAM device. So here it demonstrates that you can have multiple levels, different resistances, and then they measure the retention of different resistance, and also do this simple extrapolation to show that the potential of this multi-level operation. Okay. So this was the e-trace work. And then IMEC, the research organization from Belgium, also worked on the hafnium oxide material. And then at this IEDM 2011, it demonstrated the smallest RRAM cell, 10 nanometer by 10 nanometer in terms of the dimension. Of course, the transistor is still larger, okay, but the RRAM itself, so here from this image, from two cross-sectional image, so if you cut the device, because device is somewhere here, right? If you cut, then you have those two cross-section, the view, X and Y. So here, the device has similar structure, tinitride top electrode, tinitride bottom electrode, and then we have this hafnium oxide. And then here the capping layer is different. That's the only difference. So here the capping layer changed from the titanium to hafnium, okay, just hafnium metal, and then hafnium oxide. So again, the hafnium will attract oxygen a little bit. So that's why here it uses X, because it's below than 2. So you get a little bit of oxygen to here, then this will be oxygen deficient. So you create some, filaments, help to create some filaments in the hafnium oxide. So then let's look at the characteristics from the IMEC data. It varies the device area, because the smallest one here, we showed you the 10 nanometer by 10 nanometer. Of course, they have larger ones. For example, 1 micron by 1 micron. So they vary the area of the device and then measure the voltage. So here there's a so-called forming voltage. So this is actually still, even today, is a problem for the RRAM, oxide RRAM device. That is, for the very first cycle, you have to apply a larger voltage. This is the first cycle set voltage. We call it forming. So you have to form the filament to form the filaments. This is very first cycle. You have to basically, burn the device. They also call burn-in process. So the very first cycle, the voltage is a little bit high. Of course, depending on the thickness. The thicker the oxide, then you are going to apply a larger voltage, especially when you scale, then you may apply like 4 or 5 volts. So that's not good, because that means your preferred circuits needs to provide like high voltage, more than 3 volts. Okay, so then that's not very friendly, because you are going to use that high voltage only once. Then you have to design the circuitry, preferred circuitry, to provide that high voltage, but then it's only used once. Then after that, then the switching voltage, the regular switching voltage less than 3 volts, then it's a waste of the peripheral circuits resource in that case. But anyways, even today, I can tell you, like TSMC RRAM, we still need the forming process. So, well, of course, I don't tell you what is the voltage there, but it's confidential. But I can tell you there's forming process. Okay, so then here the forming voltage also depend on the thickness of the capping layer. The thicker the capping layer, this is a capping layer, that means the hafnium metal layer. The thicker the layer, then the forming voltage could be reduced, because the thicker the hafnium, the metal, you may extract more oxygen from the oxide. Therefore, it helps to create the filaments. So there would be a lot of engineering effort to improve this, or let's say get rid of this forming process if possible. And then after the forming, then the regular set and reset voltages actually pretty small in this IMAC data. You see that the reset voltage, set voltage is even below 1 volt. And then there's not much dependency on the device area. So even, let's say the device is 1 micrometer by 1 micrometer or 10 nanometer by 10 nanometer, then the switching voltage set and reset almost the same. That it means it's filament, it's filament, because a large device, small device, then you probably only create the same like filaments. Even you have a large device, but actual switching is very local. Okay. This is also verified by the resistance, or let's say current, for different areas, device area. Then no matter it's large device or small device, on and off current, especially the on current, is almost the same, because on current depends on the diameter of this filament, right? Even though you have a large device, but most of the area is insulating, so you only have this local filament, same as a small device. So okay, so then this is the relationship between the set and reset voltage and versus the pulse width. So here there's a slight dependency. Let's say the faster speed, let's say the 10 nanosecond switching, you need a little higher voltage, especially for the reset. You see that if you go down to 10 nanosecond, you have to increase the reset voltage, and also depending on the thickness, depending on the cell size. Okay. So generally, if you want to switch faster, you have to apply larger voltage. And then the endurance. So here, the IMAC paper, the follow-up paper, discuss the trade-off, or let's say optimization of the programming condition. So here, you see that this is a resistance as a function of the cycling pulse number. And then here, depending on the set and reset condition, for example, in the first case, it's the set is kind of weak, reset is kind of strong. So you see at the end of the lifetime of the device, then the resistance all shift up, and then there's no switching here. Device is dead. This is after 1 million, 1e6 cycles. So this is because the reset is strong, so the device tend to go to higher resistance, and then it will eventually fail at, or some people call stuck at HRS, high resistance states. Then as you ramp up the set condition, let's say set voltage, actually this one decides the compliance current. As you increase the word line voltage, which is the gate voltage of the access transistor, you are going to increase this current. So then you see that it tend to, the resistance tend to go down eventually. So for example, this strongest condition, then the eventual failure state is stuck at no resistance state, EELS, right? Because the set is too strong. So that means we have to balance the set and reset condition. For example, here IMAC demonstrated the balanced set and reset condition. So you can keep cycling even to 10 cycles, okay, in this case, while maintaining this on-off ratio. So if your programming condition is well designed, then you can help improving the endurance. And also the retention, this is a standard way or better way to do the retention as we discussed. So you have to change the temperature, right? So anyway, so at the same temperature, for example, 200C, you are going to monitor the resistance as a function of your baking time. So here there are two conditions. Let's say a EELS 100 micron, that means the compliance current is 100 micron. So this is a lower, stronger, or more stable or low resistance state. But anyway, you monitor that, and then you see that the resistance keep increasing over time. That means the filament will dissolve at higher temperature, right? So you have the filament with those oxygen vacancies. And then here the 100 micron means you have a stronger filament, pass larger current. And then this one is a weaker because it only pass 10 micron. But anyway, no matter which case, at higher temperature, those vacancies tend to move around because of the thermal activation. And then the filament will dissolve. That means the resistance will go up eventually. So here you need to monitor the time. For example, here if you define the failure criterion, let's say if this resistance increase by 10 times, then you define this is a time to failure. This is a time to failure. Time to failure. And you record this time. That will be one data point. For example, that one corresponds to 200, 200, maybe this is 200. You have to change the units. We discussed this before in the NAND flash. You have to change from the degrees Celsius to Kelvin, and then do the KB, Boltzmann constant times Kelvin, and get the 1 over KB, 1 over KT. But then here, this is in the unit of electron volts. You have to convert this to electron volts. And anyway, so here, this is the time to failure you record. This is time to failure, okay? You record from here. This is one data point. And then you vary the temperature, right? For example, 250C or 150C, then you get a different time to failure, okay? And then you draw the straight line because you are assuming this failure is driven by this thermal process, which is governed by the Arrhenius law, 1 over KT. So the slope will give you the activation energy, EA, activation energy, because you have this kind of equation, right, for any thermal process. So this slope give you the activation energy. So from this measurement, extrapolate the hafnium oxide-based system. Typically, it's like 1.2 to 1.5 electron volts in terms of the slope. And then you do the extrapolation, right? Here you have to look at 10 year. 10 year, you remember this number? At least I remember. Okay, 3 times 10 to 8, 3 times 10 to power 8 second. Okay, because here is showing in second. So the 10-year lifetime means 3 times 10 to power 8 second. Okay, so that is this dash line here. And then you look at the cross, the intersection here. For example, here, it says that if you have this weaker filament, then at 10-year lifetime, you can get the temperature like 92 degree. That means if you bake the device at 92 degree, it can have 10-year lifetime in this case. Of course, here I believe I might have done some statistic measurement. This is only the median value. Okay, at 50. So that is not the tail bit. This is the median, or let's say the average behavior of the array. So you have to account for the worst case. Anyway, this is a methodology we always use, and we already discussed this in the NAND flash, and we repeat one more time here. So you may see this kind of thing, okay, in your what is left final exam, okay. I want to repeat. Okay, so then let's talk about the physics of the RRAM. So when I started the RRAM research back in 2007, 2008, at that time, even though there are many papers showing this behavior, but then the physical mechanism is unclear. So my PhD thesis spent a lot of efforts to clarify what is the device physics there. So, and those proposed mechanisms later was widely accepted by the field and used, even some of the models was used by the industry, including TSMC. So that's my contribution to this field. Anyway, so here, this is what we proposed. Initially, the device in the fresh state, then even though you have some as fabricated oxygen vacancy, but still it's quite insulating. So that's why you need this forming voltage to knock out the oxygen atoms. And then oxygen atom, because here you have positive voltage, then this oxygen atoms will carry the electron, will become oxygen ion. And negative charge oxygen ion will drift towards the positive biased top electrode. So then what is left here after the forming process? Then you have this conductive filament with the oxygen vacancy, like a circle. So this is like electron hole pair, right? You get the electron there, then you leave a hole. So here we don't call it a hole, we call it a vacancy, oxygen vacancy, okay? So after the oxygen ion reach the top electrode, then it will give away the electrons to the external circuitry, external like the loop, right? Because you have this loop, right, for the electrons to flow. So here, then what is left is the oxygen atom. So that means you are going to have some interfacial layer, or sometimes we call oxygen reservoir, to basically store those oxygen at the interface. So that's why here if you have a metal capping layer like the titanium or hafnium, it will help to maintain that oxygen, because you can partially oxidize that metal layer. So in the reset, then we apply negative voltage. Okay, the negative voltage will drive the oxygen ion back. Right, negative voltage will drive this away. So then this oxygen ion will recombine with oxygen vacancy. So after recombination, then you will recover this part. So here, in many cases, you won't recombine the entire filament. Only a small portion will be recovered. And then after that, the electron will tunnel through here. So the tunneling current exponentially depend on the gap distance here. So, but anyway, this current is exponentially smaller than here you have the full path. Okay. So in the next cycle, then we apply positive voltage again, and then we will recreate these filaments. But here the thing is that this is a stochastic process. So every time when you create this filament, the shape may vary a little bit. That will give you the variation in terms of the switching voltage, in terms of the resistance values. So that's the fundamental mechanism. you cannot get rid of that because the atom movement is not under your control. Okay, so then this is, of course, the hypothesis we proposed at that time. And later, the research community verified this mechanism through some very dedicated experiments. So for example, this is one nice work done by IMEC. And what they did here is, again, this is my IMEC memory stack. So they want to observe the filaments, okay, experimentally. So what they did is that, okay, so here they are going to program the cell, let's say do the forming set resets through the standard operation. And after each operation, they will peel off the top electrode. In this case, they do it from the bottom side. Anyway, they are going to peel off the electrode. Okay, remove the electrode through some very dedicated process. And after that, then the hafnium oxide surface is exposed. Then they are going to use this so-called conductive AFM, conductive atomic force microscopy here, to scan over the surface of the hafnium oxide. This is conductive, so then it can measure if there's a current flowing through. So let's say you have this device, right? You have some local filaments underneath. So this tip of the CFM tip, there is a tip. If there's current going through, then this resolution is pretty high, like in the nanometer scale. So you scan over this surface, right? If there is a conductive spot, then it will show up. So here you see that in the fresh sample, so here the color is a little bit weird. There, let's say no current is red, and with high current is blue. It's kind of counterintuitive. But anyway, so here in the fresh sample, no currents across the entire sample. But after set, you see that here locally in the middle, it has some high currents compared to the other region. So here it measures the filament size, diameter is like 30 to 50 nanometer in terms of this in the middle part, right? And then after reset, you see that this shrink, the filament shrink to almost disappear, right? And then current reduce. So it verified under this device surface, then there's local conduction filaments, right? This is from the top view, right? From the top view, you scan over the device surface. The key is that you have to remove the electrode, because if there's an electrode, then the electrode will, equal potential, right? Everywhere will be conducting. So you have to remove the electrode, right? This is from the top view. And then later, people also try to do this from the side view. So this is another nice work. And look at this side view of the device. So here you are going to cut the device. You have the device, right? You have to cut. Yeah, cut. It's hard to draw. But anyway, it's a cross-section of side view. So then here, this is under TEM. And the technique they use is called EELS, electron energy loss spectroscopy. So this will look at the oxygen concentration. Okay, so here it's a little bit hard to read, but anyway, so here this the sense stack, like MX stack. So here what they found is here locally in this region, this is within the hafnium oxide region. the oxygen, the redness here is let's represent the concentration of the oxygen. So here is oxygen deficient, the color, less red. That means less oxygen there. That means oxygen vacancy. You are missing oxygen locally there. While on top, on the hafnium, on the same region, in the hafnium capping layer, you also see less hafnium here. Hafnium and deficient, because here part of the hafnium oxidized. That means oxygen is coming from here to here. You have this local migration as we proposed in the picture before. You have the local migration of the oxygen. So this is a very subtle, experiment to deal with. Anyway, so then the filament is around like 10, 15, 20 nanometer typically in that dimension. Okay, so this is a direct evidence of the oxygen filament, okay? Oxygen vacancy-based filament. And then the electron conduction mechanism, once you create the filament, then the electrons can turn through, because the vacancy, each vacancy is like a trap site for the electrons. So the electrons between two electrodes through the oxide could have many conduction mechanism. So here from the band diagram, you can see that first one is the thermal emission. Second one is what you are familiar with now. Let me ask, what is the second mechanism? That's FN turning, right? And then here, but what is here? The FN turning is not the dominant mechanism. So what is dominant thing here is this one. Because you have so many oxygen vacancies, so the electrons is like a stepstone for the oxygen, for the electrons to go across the oxide. So here then you have this trap assisted tunneling. The number 7 is trap assisted tunneling. Okay, this is a major conduction path. Okay. So then later people try to reproduce this dynamic process through the modeling. And also even in my PhD work, I have done some of those kinetic Monte Carlo modeling, try to model each atom's movements. And here is a nice work from a group from Italy. So what they did is to run this atomic simulation. So here, what you see here, this red dot is the oxygen vacancy. As fabricated, you have some like intrinsic vacancy, but when you apply the voltage here, you're going to create more and more vacancy. And here, by the way, here the red one is the vacancy, and then the blue one is the oxygen ion. It's like a pair, right? So here, beyond the intrinsic vacancy by the fabrication, then here, when you apply the voltage, you are going to create oxygen and the vacancy pair. And then here locally, the temperature will also increase because of current flow, Joule heating. And then the electric field and also the temperature will help the oxygen to migrate and then to the interfacial layer. So in this case, they use titanium as a capping layer. So here, then they have the concentration along this direction. So at the end of the set process, you have a high oxygen concentration in the interface, okay, as we proposed. So that's why they can model the IV characteristics and then correspond to the different configuration internally. So you see the filaments and then the interfacial like oxygen accumulation. So this is some modeling work, try to visualize what's going on. Okay, so then I would say by the time like when I graduate from Stanford with my PhD 2012, 2013, the physical mechanism is almost clear. Of course, there are some subtle, details, but overall, the physical mechanism clear, and then also industry converge the material choices to those few, as I mentioned earlier, like hafnium or tantalum, or the mixture of those. So after that, then the array level integration starts, and then the chip demonstration starts. Okay. So first, material and device physics, individual device, optimization, right? And then measure the key properties like endurance, retention, and after that, people move to the array level integration. So, but even before that, because I mentioned that ITRI was the first pioneer to demonstrate the hafnium oxide RRAM. So then 2 years later, this is at 3 years later, ISCC 2011, ITRI demonstrated the first RRAM prototype chip, okay, based on their technology. So as I said earlier, so the access transistor 1T1R is at older generation, but even at that time, it's not that bad because this was, for 13, 14 years ago. Or 180 nanometer CMOS, and then the entire array is 4 megabits, and then here is a device typical characteristics, and this is nothing different from the IEDM paper. So here, what is interesting is this 2-bit per cell demonstration at the chip level. Okay, so here what they did is this write and verify. This is similar to the NAND flash. So when you program the multi-level state without the verify, then the distribution in terms of resistance may have some overlap in between. Right, you need to encode 4 levels into 2 bits. So here, then they need to have this verify pulse, right? It's not single pulse programming. You have to program it, read it, reprogram it. So after a few verification pulses, then they can open the gap between the states, and then they can encode those 4 bits. But because they have to apply additional pulses, so the latency, increases, right? If you only do like a 1 bit operation, that's a very high resistance, a very low resistance state and very high resistance state, you don't need to, because the gap is large, you don't need to, verify. You can do that within 8 nanoseconds, even at a chip level, including the VLAN decoder, whatever, the peripheral circuits delay. You can do read and write with 8 nanoseconds. Okay. But with the verify, of course, then everything slows down.
So these levels have different extended. Is it the similar one that you were talking about before, where there were different LRS states that were
Yeah. You can use different, for example, VLAN voltage, as I said earlier, to control the compliance current, and then you can get different resistance.
The verify step is related to that? Or is that too?
The verify is to, tighten the distribution across the array because you have so many cells, right? You have variations. You have to tighten that. It's the same as NAND flash. It's the same as no matter which technology we're going to talk about, as long as it's non-volatile memory, no matter NAND flash, RRAM, or phase change, MRAM, whatever, you have to do this if you want to do the multi-level operation. There's no way you can get rid of this verification. So later, Panasonic from Japan also invest in this RRAM technology. And actually, there are quite a few groups in Japan and doing the RRAM at that time. So here they choose the titanium oxide, okay, bilayer structure. And they demonstrated here also a prototype chip around like 2011, 2012 at that time. So here, the key is that they use, I should say 1S1R. So they have this bidirectional selector, okay. This is cross point array. This is not 1T1R array. They have this kind of selector. They call diode, but actually it's a bidirectional selector because you see the nonlinearity ratio, right? We mentioned this n value, 150 in this case. So this is integrated with R1. So you see here the selector and R1 selector. What's the symbol for that? It's a bidirectional diode plus the resistor R1. So here is 8 megabits, the entire chip. And also the peripheral CMOS is 180 nanometer technology nodes. And overall, the chip I/O provide like 400 megabytes per second write throughput. It can access 64 bits in parallel, and each write operation is like 17 nanoseconds, so you can get this throughput. And also the retention is pretty good. So you see they do this at least 85 degrees C. Entire chip can satisfy 10-year lifetime. So here then, Panasonic even commercialized this, okay. At that time, you see that there was a news. The MCU microcontroller used this RRAM, exactly this one, okay. And this is from like, kind of like DigiKey or, this kind of online retailer. You can buy it with this MCU with the RRAM. I don't know if they discontinue maybe today, but this is available at that time, okay. And this is what we discussed before. This is even larger scale integration because previously those are the megabit level. And this is a totally another scale, right? 32 gigabit chip. Already talked about that in the previous lecture. So I will skip that. This is from SanDisk. Actually, this is jointly developed by Toshiba as well. I didn't mention Toshiba, but Toshiba also spent effort in this integration. And also at that time, there's a CB-RAM activity from Sony and Micron jointly developed this technology. So here the active electrode is copper with some ternary here. And then the total chip size, again, this is at larger scale. They want to use it for the, the storage class memory or something like 3D points. But anyways, for the Sony and Micron, this actually is 1T1R, I believe. Yeah, 1T1R. And it's more like in the DRAM process, 6F squared DRAM process. Instead of 1T1C, they use DRAM's layouts to do this 1T1R, and the tech node of that DRAM half pitch 27 nanometer at that time. So total chip size 16 gigabits, and then here is the read performance. You see that at this larger scale, it's kind of slow, right? 2 microsecond, 10 microsecond. So it's slower than the megabit. Megabit, you see the previous demonstrations easily like 10 nanosecond also. So here it's larger scale than like microsecond. But anyway, so those developments was dropped by those companies after those demonstrations. So Toshiba, SanDisk, and then Sony Micron, they didn't continue the efforts. So then what really, and also Panasonic, those kind of small business, right, compared to other major semiconductor companies. So that's why, I mean, around, let's say 2014, 15, 16, 17, those few years, RRAM research and development, it can go in to a valley, and you know, this typical, they call what, this Gartner curve, this hype, right? So you are going to, so it's like this, right? This technology like development, right? So let's say for RRAM, I would say here start from, let's say 2004, 2000, let's say for the hafnium oxide based 2008, and then the peaked at like 2012, and then 2016, and here like 2020, something like that. So yeah, so who really picked up here? Guess who really picked up? Of course, I mean, as a university researchers, like for example myself, spend a lot of time here, try to, you know, understand this technology. And then here, this guy, TSMC picked up. Okay. So of course they have done internal research and development, you know, maybe in some stealth mode, right? But they didn't publicly talk about that until like 2017, 18, around that time. So I would say TSMC's technology probably in essence, I mean, initial version came from the E-tree. Even the E-tree, the people I know who developed the very first generation of that, the first few authors, they are my good friends. They all joined TSMC, so I know. So that's why TSMC stay with that hafnium oxide technology and try to ramp up and make it compatible with their platform technology. So here, this was the first publication by TSMC. This is ISCC 2018, integrated at 40 nanometer process. Okay, so here, if you look at the data here, actually, it's not as good as what E-tree published at very early days in terms of, for example, on-off ratio. So here you see the on and off, this is current ratio is pretty small. It's no longer like 100, only like a few times. But here, this is from the major foundry. What they want to optimize for is to make sure the yield and then make sure the entire array works, okay? Because for the early publications, probably it's a small scale demonstration, and also it does not really guarantee the yield and so on. So for foundry, their business is not to, you know, optimize a particular property to the very, very large value, then looks good in the paper. Then that's not their target. They want to make sure this entire thing work. Okay. So anyway, so here this entire thing work. Okay. And then here are some details of the array size. It's a 256 kilobit array. And then in the cell size actually is large. The 1T, 1R. Here the T might be large because the current to program the RRAM is kind of large in this particular case. So the transistor size is not the minimal size. The W/L is not 1. Okay. So then the total cell size like 50 F squared. So this is like 3 times better density than the SRAM as a same technology node, 40 nanometer SRAM. But anyway, so they have done a lot of reliability testing under different temperature and different cycling and so on. So anyway, this was the first publication. And then this technology was pretty mature now.
Why are they calling it embedded RRAM? Is it because they're trying to like
embedded, right? So this is all embedded with logic. Embedded means with logic, right? Embedded means logic. SRAM, embedded, right? We talk about embedded, the definition at the very beginning of the semester, right? Standalone, off-chip. Your off-chip DRAM, off-chip NAND flash, off the processor's chip. Embedded with the processor's chip, okay?
But at the start of this chapter, you mentioned that typically RRAM was to like more closer to NAND flash, like storage.
No, that's wrong. That's why those business fail there. The real commercial interest is here. So that's why like Micron, whatever, Sony or the SanDisk, they drop the business because their initial target was wrong. They try to make it like a 32 gigabit or whatever, try to make it large scale. But then there's no cost advantage compared to the NAND flash. Right. So that's a wrong business direction. Anyway, so that's why the only commercial success today is this TSMC RRAM for embedded application, mostly for automotive electronics. So if you, I will talk about that later. But anyway, for this 14 nanometer RRAM, actually even my lab here at Georgia Tech, we have collaboration with TSMC, and 5 years ago, soon after TSMC published this paper, 2018 and 2019, TSMC came to me, and we started the discussion, and then they offered me this process. So my lab has taped out 3 generations of the RRAM computing memory chip with this platform. And I can guarantee you this RRAM works, okay? And computing in memory, I mean, whether it works or not is a different story. It works, okay? But then with many, many tricks. But for the memory, this is good technology, okay? I can guarantee you as the user, okay? So at the same time, Intel also tried to invest RRAM. So they published the ICC paper 2019, 22 nanometer RRAM with their FinFET technology. And then here there are some details. I'll skip those, let's say the characteristics. You can read the table. So here you see this is RRAM stack, and here is the FinFET. Here is the FinFET. Okay, 1T, 1R. R is here. Okay. So here then they have this macro as well, and even they showcase the layout. Okay, you see that they have like 4 fins to drive this one, and then the RRAM is at metal 4, and then the total cell size, because you have 1T, 1R. Mostly you see RRAM is small, the transistor is large because you have so many fins here. So the total cell size you see like 200 by 200 nanometer. Okay. So some more, larger view of this cross section. So RRAM is very little here. So it's very little here, like between metal 4 and metal 5. And the underlying is a transistor very small, and then above that is high level metal, global metal for your power supply and so on. So it's very large on the metal 8 in this case. So more views. Pretty nice images here. Okay, so here I try to summarize the TSMC also later published, migrates this technology from 14 nanometer to 22, and now 22 is their main commercial offering. And they offer both 40 and 22, and their target is embedded flash, E-flash replacement as an embedded non-volatile memory, mostly for the microcontroller, where you need the on-chip non-volatile memory. And then all of them 1T, 1R, and then the cell size is kind of 15 F square, and then on resistance, some of them didn't disclose, but roughly speaking, a few kilo. On-off ratio is not like 100 or 1000. From the foundry is like a few times to 10. And then some of the papers report the voltages, typically like below 3 volts, okay, up to 3 volts for the forming, but the normal operation is below that. And then here the rate, a few nanoseconds. Endurance is like, you know, it's like NAND flash. It's not super high. It's not like a 1E12, okay? So this is for this particular eFlash application, good enough, because the embedded flash, a floating gate transistor with the logic, I'm not talking about the NAND, the separate one. I'm talking about there's embedded flash. The latest technology you can have that is 28 nanometer. Below 28 nanometer, industry thinks it's impossible. The increased mass cost and then the physics there. So that's why industry want to have the RRAM and later what about MRAM, similar targets, is to extend the embedded non-volatile memory beyond 28 nanometer. For let's say 22 nanometer, even 16, 14, 12 nanometer, even 7 nanometer on the roadmap to have the non-volatile memory option for embedded applications, especially for the MCU. So here, the latest progress, this was this year. So this actually to my surprise, because I thought the RRAM scaling has been on that 22 nanometer for quite a few years. There's no recent updates. But this year, TSMC shows that they integrate the RRAM with 12 nanometer process. Okay, so here are more details. Yeah, so you can read the paper if you are interested in that. So again, this is megabit level embedded non-volatile memory targets. So some more details from this paper. So the RRAM between Metal 4 and Metal 5, same as Intel. So by the way, Intel, I think they didn't continue the RRAM after that publication. So yeah, Intel is they have their own problems to deal with. So anyway, so right now commercially, I don't think this one 12 nanometer is commercially available. This is still very early stage publication. So what TSMC is offering today commercially, 40, 22. Okay, maybe they have 28 nanometer as well. Yeah. But anyway, so here are some results from this paper, and yeah, again the challenge is to improve the gap between those two states, especially as a tail bit. So here we're talk about the ppm is the 1 per million, right? So you're talking about the tail. The majority of the cells, I mean, they're okay. So what the industry tries to improve is the tail. That's always out of the 3 sigma, even 6 sigma distribution. So here, this is the summary. So okay, the tangible application I have to emphasize. Okay, it's not that NAND flash or whatever you are thinking of. So it's embedded non-volatile memory with 1T1R, and TSMC has a volume production for those technology nodes, and it's ramping up 12 nanometer. Okay, they have large orders. For example, here there's a news that Infineon has a big order with TSMC RRAM. So this is commercially viable now. And improve the device uniformity and reducing variability is still needed. You see that how industry is trying to deal with this tail bits. 10 out of 1 million cells are behaving like this. So you have to deal with that. Of course, you will have some ECC error correction code, but fundamentally, you need to improve the device distribution. So here, one challenge moving forward, even for TSMC's RRAM, the current So the reset operation is still too high. That's why you need large transistor to drive that. As I said earlier, the RRAM cells could be small. Even iMac demonstrated 10 nanometer by 10 nanometer is possible. But then the transistor is large because you have to provide enough current. So fundamentally, we have to reduce the current below 10 micron. Therefore, the minimal W/L could be used to provide the current. Otherwise, you have to use multiple fin and the cell size will be large. Ideally, if you can increase the endurance to this level, that would be fantastic. But currently, it's like 1E3, 1E4, 1E5 for the industry offering. Okay. All right, so that's it. Any questions? Okay, all right.